For the third talk of the morning, we have Kostas Skenderis from Princeton, who's going to speak on the supersymmetric completion of the R4 term in 2B supergravity.
Which one? Oh, thank you. Okay, today I will talk about a work to appear hopefully this month, which is done together in collaboration with Sebastian De Haro and Anna Maria Sinkovits. So the outline is as follows. I will first motivate this work, and then I will present the results. And after I present the results, I will go back and try to briefly outline how we derive them. So I'll first briefly review type 2B supergravity, both in components and in superspace. And then I will use these results to show that all fields fit in one superfield, which I call the dilaton superfield. And I will use the superfield to construct a superaction, which is basically contains what I would call the superpotential of type 2B supergravity. And for this construction, one needs to construct also a chiral measure, and I will show you how to do this. And then after going through this, I'll show you how to take the superaction and derive the resulting components. And I will finish with some results about manifest SL2Z invariance versus manifest supersymmetry. Now, the motivation. Well, string theory in low energies is well approximated by supergravity theories, but string theory is not, strings are not point-like particles, and the effects of the massive string modes, the leading effects at low energies are encoded by certain high derivative corrections which have a well-defined coefficients. So, for instance, in type 2B theories, the leading effect is given by a specific R to the 4 term, and there are lots of other terms included here. So since these are the leading string effects to low energies, I believe these are important to understand both their structure and also their implications. So I will start by first briefly mentioning what sort of things I have in mind, and then I will go back and discuss in detail the structure of these terms. Now, all of these terms are important if we try to study dualities that go beyond the leading supergravity approximation. And in particular, if we, in ADS-CFT duality, this capture 1 over n and subleading terms in the Toft coupling limit corrections. And this will be corrections both to results such as temperature or results like subleading terms in correlation functions. Now, these results would also lead to stringy corrections to supergravity solutions even away from the near horizon limit. So using these results, one could derive corrections to all kinds of supergravity solutions, in particular corrections to solutions that lead to black holes. And then using these results, one could try to study the properties of how physical quantities behave under string theory corrections. At the same time, these results may allow to evade the no-go theorems that tell us that you cannot have de Sitter compactifications in supergravity. And they may also lead to stabilization on moduli. In particular, in the previous talk, we've seen that there's these compactifications which involve flux and lead to not-scaled supergravities, where to leading order there is no cosmological constant and supersymmetry is broken completely, but there is still an unfixed moduli. Now, if we include these first corrections, these alpha prime corrections, there is no reason for the cosmological constant to remain 0, and it is conceivable that this would lead to potential for the remaining moduli. Okay, so that's more or less, that's the sort of things I'd like to do once I know all the corrections. So let me now go back and briefly review how one computes these effective actions. So there are two known ways to compute the effective actions of string theories. One is to do sigma molar computations, and the other is to do scattering amplitude computations. In type 2B string theories, the leading corrections arise either for 4 loops on the on the worksheet, and it's 4 loops because there is an alpha prime cube there, or from scattering amplitudes. And the scattering amplitudes involve 4 points or higher. For instance, the R to the 4 term comes from a 4-point graviton scattering amplitude. Now, there was a lot of activity in deriving this sort of corrections in about 20 years ago. But despite all this effort, the full set of such terms has not been determined and is not available. So the purpose of this work is to provide all these terms, to provide all the terms that relate to the R to the 4 term by supersymmetry. And I will do this by constructing these terms in superspace, but I will also later on go back to components and show how they look like in terms of normal X-space fields. So, in particular, we're focusing in type 2B supergravity. Now, the type 2B effective action has the schematic form. So here I denote with S naught the Litting terms, even though there's no covariant Lagrangian that from where all field equations can be derived. I can schematically still denote them by S naught. And the Litting corrections are the ones with pink. Now, because we have the freedom of field definitions, these terms here are only defined up to the lowest order field equations, because I can redefine my lowest order fields with phi I denote generically all the fields by some alpha prime cube dependent coefficient, and this is going to shift this coefficient in this manner. So in order to eliminate this ambiguity, I'm going to work with on-shell superspace. So even if there is no off-shell superspace in 10 dimensions, even if there would be one, then it would be preferable to work with on-shell superspace just because of this reason. So what I'm going to derive is that all these alpha prime corrections are captured by a formula of this form, where here we integrate over half of superspace, so it's d16 theta. Delta is a supersymmetric generalization of the measure, which schematically is of this form. So the Litting component is the square root of the metric. And then the next component in the theta expansion is the gravitino, etc. I'm going to discuss later on in more detail how to derive the chiral measure. And W phi is what I call the superpotential of the type 2B supergravity. And phi is the dilaton superfield, which I'm going to discuss now. Now, the physical fields of type 2B supergravity can be thought of as parameterizing the coset space of SU1, 1 mod U1. So here I put an SU1, 1 matrix, and these two components represent chiral superfields. Namely, they satisfy this equation, where the other two are anti-chiral superfields. And I will show you later on that all the fields of type 2B supergravity can be found in the components of these superfields. Now, in terms of these guys, the superpotential take this form that I've written over here, where this CNs are just some constants. So in particular, the R to the 4 term is contained in this little term over here. Now, the other terms, so the type 2B supergravity at the classical level has an SL2R symmetry, and the compact subgroup of this is a U1. Now, the type 2B string violates this U1, but nevertheless, the terms can be organized in terms of superselection rules, in terms of their U1 charge. So all the other terms are the terms which violate the U1 charge. So in particular, for instance, this term over here violates the U1 charge by 2n minus 8 units. So once we determine, so this is a superspace formula for the corrections. Now once we have this, then the next question is how do they look like in terms of X-space fields. So I'm not going to give you all the details, but we do provide in the paper all necessary formulas in order to obtain the component action. In particular, if we just focus on the term that contains the R to the 4 term, which is basically this the single term, then, and if we only focus on bosonic terms, then the structure is roughly the following. So The simplest terms to consider are the terms which only depend on the metric and the F5 form. So there are lots of terms that depend on the three forms, which I'm not writing here, but the other terms are roughly of this form. Namely, we have some generalization of the Riemann tensor, or better, the Weil tensor. So this curly arrow starts with the Weil tensor, and then we have some contributions for the F5 and also some contribution from the three form. Now, the first two terms were anticipated previously using linearized superspace. But the next ones, the purple ones, are ones that follow because we use results at the nonlinear level. In particular, these terms here imply that terms of the form s cubed f5 squared or c squared f5 to the 4, etc. So these terms give new contributions to 4-point functions in ADS-CFT correspondence. In particular, they don't contribute to 3-point functions. That would be a contradiction, since we know that 3-point functions do not normalize. And here I'm very schematic. Now, there is a very specific contraction between the F5s that make this possible. So these are the results, and then in my remaining time, I like to derive those. So I will start by briefly reviewing type 2B supergravity. So throughout, I'm working in a complex basis. So the field content is given by the metric. We have a complex 2 form and a real 4 form, 2 complex gravitino and a complex scalar. Now the classical theory is invariant under SU1, 1 or SL2R symmetry, and this SL2R becomes SL2Z at the quantum level. In particular, this complex scalar field A parameterizes this coset model, and in order to realize linearly the SU1, 1 invariance, I'm going to add an extra scalar, phi, and an extra local U1 invariance. So then the form of the matrix I showed you before is given by this. So here we have the physical scalar, and here this is the extra scalar phi. Now the extra U1 invariance is a U1 invariance that acts from the right. So we multiply with the U1 transformations from the right, where the SU1, 1 acts by matrix multiplication from the left. So in this work, we're going to work in this gauge invariant formulation. And it's important to know how the various fields transform under the various symmetries. So we have, I think it hasn't been appreciated too much in the literature that there are two different U1s. One is the local U1, which one uses in order to realize linearly the SU1, 1. And there is a second U1, which is the rigid U1, which is the compact subgroup of the SU1, 1. So here in this table, I put the charges of all the fields under these two different U1s. And this zeta here is the supersymmetry parameter. Now the scalar field A is invariant under the local U1, but has charge 2 under the rigid U1. Now this scalar field A is related to the dilaton and action field that we use in string theory by a nonlinear transformation, which is basically this one. Now since A itself is invariant under the U1, then tau is invariant as well. So tau is invariant under the U1, but tau itself transforms nonlinearly under the rigid U1. So for this reason, in most of my formulas, I'm going to use the A rather than tau, because if I use A, all the formulas will have nice transformation properties under the rigid U1. So this was a brief summary of the type 2B supergravity, the fields and the symmetries, but I'm going to use type 2B superspace. Now, in superspace, we promote for every field, we introduce a superfield. So for the small u, we introduce a capital U, and I'm going to use this notation that when I capitalize a quantity, then the leading component is the X-space field. And Z denotes the superspace. In superspace, you have 10 x's, and we have some complex fermionic coordinates. So the theta is a complex 16-component Wald spinor. Now in superspace, the geometry is encoded in the algebra of supercovariant derivatives. So if we take the commutator or undercommutator of the two covariant derivatives, this gives back a supercovariant derivative with the torsion, and then we have curvature terms. Now in type 2B superspace, the local symmetry is the Lorentz group across a U1, and this generator here corresponds to this U1. And this U1 we identify with the local U1 that we introduce in order to realize linearly the SU1, 1. So now once we have this, then the next step is, now all these guys here contain far too many components to just describe type 2B supergravity, so we have to impose some constraints. The next step is to impose covariant constraints in order to reduce the number of independent components to the components of the type 2B supergravity. So this has been worked out by Han West. So this is roughly how the superspace looks like. So if it would be just flat superspace, then the only non-trivial commutation relation would be that one, namely two fermionic derivatives go to one bosonic one. But then once we go to curved superspace, then we get lots of more non-trivial commutation relations. And we see here that all the fields of type 2B supergravity appear in the torsions. So in this one we find the Latino, here we find the complex 3 form and the 5 form, and in this one we find the field strength of the gravitino. And these relations here contain also lots of terms which are bilinear in the fermions, which I don't display here. Now to derive these relations, one basically has to take these covariant constraints and plug them in the Bianchi identities, which now become non-trivial equations because the covariant quantities are constraints, and then solve the Bianchi identities. Now solving the Bianchi identities, one obtains both all the supergeometry data, namely the torsions and the curvatures, and also obtains all the fermionic derivatives of all fields. For instance, the fermionic derivative of the V field, which is a part of the D-Latin multiplet, gives the Latino. Finally, in this case, in 10 dimensions, the Bianchi identities also imply the field equation. So this is an on-shell superspace. Now, once we have this data, once we solve the Bianchis, we can obtain all information we want to about component fields. In particular, we can obtain all components field by the method of projections. So if we set all the thetas to 0, we get the limiting component, then we take the derivative of S, and then this gives the first component, etc. And we can also obtain the supersymmetry rules, which this is given by this formula. So for this one, it was important that the Bianchi identities determine also all the fermionic derivatives of all fields. Okay, so now we know what is the type 2B superspace. And then the next thing to discuss is how do the fields fit in supermultiplets. So one of the simplest supermultiplets that one has in flat space are chiral supermultiplets. So in flat superspace, one can always impose this linear constraint of this sort, which we usually call chirality constraint. In 10 dimensions is probably more appropriate to call it analyticity constraint because both these have the same chirality, but I will still use the name chirality because of the similarity with 4-dimensional physics. However, in 10 dimensions, in curved spacetime, such constraint is not always possible. Actually, generically, such superfields do not exist. So the constraint arises because the undercommutators are now non-trivial. So if this is satisfied, then the undercommutators should also be 0. But we know from the algebra that this is given by torsion times some covariant derivative. So generically, if this torsion is non-zero, then this would imply that phi should be annihilated by the other derivative as well, which generically would imply that phi has to be just a constant. And in type 2B superspace, indeed, this torsion is non-zero. So if we work out the right-hand side, and actually I give here the exact relation, one finds that the only superfields, chiral superfields, which are possible are the ones that satisfy this relation, which imply that their derivative should be proportional to the d Latino. So the only possible chiral superfields are the ones which they have a Latin component, which supersymmetry variation gives the d Latino. So basically, the only ones possible are the ones which depend on v and u star. So this general and this depends only on v and u star and not on derivatives. So in flat space, if we have a superfield, then its bosonic derivative is also going to be a chiral superfield. That's not true anymore in curved spacetime. So this w has to be only a function of v and u star and not the derivatives thereof. So now once we have this the superpotential, the next question is whether we can write down an action for that. So chiral superfields in 4 dimensions are usually integrated over half of superspace. Now in supergravity theories, the measure also transforms under supersymmetry. So so one would need to construct also the appropriate chiral measure delta. So the superspace action that we constructed is this one, and in this formula I have to tell you what I mean by d16 theta, and I also have to tell you what I mean with delta. I already explained the w phi. So with d16 theta, we really mean this expression, namely we take the 16 d's, and so this is the antisymmetric, fully antisymmetric product of 16 d's. And the delta we're going to construct by imposing that this action is supersymmetric, as I will show you in the next transparency. Now, the novelty in this case, as opposed to 4-dimensional physics, is that the chiral measure itself is not a chiral superfield. And it's not a chiral superfield because the derivative of delta is basically the gravitino, and we've seen a couple of transparency ago that the chiral superfields have to go to the d Latino. So to construct the measure, we first work out, we push in all the derivatives, so basically this is now a component action, and then we require that this is supersymmetric. So this condition can be organized order by order, and we require this supersymmetric for any superpotential. So this condition fixes all the components, uniquely fixes all the components of delta, and the schematic formula is given over here. So once we know the d minus 1, then we take the supersymmetric variation and we pick the z component of this. And there are some bilinear terms as well. And now the terms depend on the complex conjugate of z should cancel automatically. And we check that this is indeed the case in the first 2 orders. Finally, there is an additional requirement. The measure carries 8 units of U1 charge. So for gauge invariance, we need that the W carries 8 units of plus 8 units of U1 charge. So the general form would be of this form. So this factor here can be thought of as a U1 compensator, and A is A itself is gauge invariant. Now, the form of W is determined by matching with known results from the literature, and I already indicated what is the form in the summary of the results. Basically, W tilde is a polynomial in this A superfield, and this can be rewritten also in this form, and this matches with results of Mine-Green collaborators, where they use a superfield which is a linearized version of this one. So from here, then we can go to components, and to get the components is sufficiently to tell you what are the components of V, because the components of U star are determined from the ones of V because of this relation. So all these components can be determined iteratively, and here they give you the first few. So basically, yeah, we have explicit iterative formulas how to get all of those. So once you have this, you have to go back to the superspace action and plug them in and go through the algebra. Now, the superpotential, this one that I gave you over here, is not a SL to Z invariant. Now, it is known from component computations that SL to Z invariance requires the introduction of non-holomorphic modular forms as the coefficients of the component fields. In particular, this depends both on tau and tau bar. But I already told you that tau bar is an anti-chiral superfield, but tau is a chiral superfield. So I can't put them in the same chiral measure. But at the same time, it is known that because of this, the tau bars and the non-holomorphic modular forms, the supersymmetry rules themselves have to be modified. So this is the invariance of the action. I mean, so far, I only use this equation with this term to 0, but the introduction of tau bars requires that there are some non-zero corrections to the supersymmetry rules, these delta 3s. But once we modify the supersymmetry rules, this means that the type 2B superspace is also modified. And these corrections to the superspace have not been worked out. So in order to reconcile manifest supersymmetry and manifest SL to Z invariant, one has to go back and first compute the corrections to type 2B superspace. And I expect that the construction that I presented here would generalize to this case. So here's my conclusions. So I show you here how to construct superpotential of type 2B supergravity using a type 2B on-shell superspace. So these terms are deleting string key corrections to type 2B supergravity, so I believe they deserve more attention than it has been so far. Now this construction should generalize both to type 2A and M theory. Finally, the terms that appear at order alpha prime fifth, for these terms there should be also a superspace representation in terms of some integral over 3/4 of superspace. So there should be a similar construction, but now one should integrate over 3/4 of superspace. And finally, there are lots of applications, and I hope to return to this.
Igor Bandas, Valencia University. As I understand, your superpotential does not produce equations of motion. I mean, constraints. And the snow is just a component action, so you have no superfield representation for S0. And if you write down your new terms in terms of components after integration with respect to theta, then you should derive some corrections to supersymmetry rules. Did you use this?
This would give us.
And can you comment about relation with recent? Okay.
Suppose you know the.
About the supersymmetry, the corrections of the supersymmetry rules. Yes, I think it will. You see the problem here, if I go back here, so if I know these corrections, this is going to give me the corrections to type 2B superspace, but at the same time, if I also know corrections to the S3, this would also help me to determine all the necessary delta 3s. Now, the computation itself, there is a straightforward way to compute these corrections. one has to go back to the solution of the Bianchis and relax some of the torsion constraints. This computation is very complicated. It's very tedious, straightforward, but it's very tedious unless one has some more input.
But I'm suggesting that the extra input would be something like exact knowledge of the imaginary one.
Yes, I think that would be useful.
How is the self-duality of the phi form built into this formalism?
Self-duality is built in because the on-shell superspace automatically has, so all the systems automatically satisfy their low order equations, in particular the self-duality. But I do want to make one comment on this, which is related also to the first question. Once one includes these extra terms, then the F5 is not going to be self-dual. There's going to be a correction to the F5 field equation as well.
On that alarming note,
Martin.
oh no,
Perhaps I didn't understand. There's an r to the fourth at tree level with an e to the minus 2 phi, and there's one at one loop. Are you able to supersymmetrize them both independently?
Yes. So this formula here, so the question is more about say the fine fraction of the W phi. So there will be a term which is a three-level term, there will be also a one-level term. What I'm not able to do is I'm not able to do at this point the contributions due to the instandence, and that's because this have to involve the modular function.
Can you show there's no two loop?
So this formula doesn't tell me whether there is a one or two loop.
okay, we could continue discussions privately at this point, I think, and thank the speaker again.